Welcome to Efiwe, excellence without stress.
Hi guys, we're back again, and today our topic is electrical energy and power. Electrical energy and power. We've already explained work, energy, and power in our previous classes, and today we're going to talk about the electrical energy and power. So, electrical energy. What is electrical energy? What is electric energy? Electric energy is the most important form of energy, and it is widely used in almost all the electrical devices around us. These devices have ratings written on them. That rating is expressed in watts and intuitively explains the amount of electricity the device will consume. Bigger devices like AC, refrigerators, it is a consume more electricity and thus come with a higher rating What is electrical energy? You already know that energy is the ability to do work, but now we are referring to electrical energy. Electrical energy is the work done in moving a charge from one point to another in an electric circuit. So electric energy is the work done in moving a charge from one point to another in an electric circuit. It is the work done when a quantity of charge moves between 2 points of different potential differences measured in joules. You know that electrical energy is measured in joules. So energy itself is measured in joules. Electrical energy also is measured in joules. In simple terms, energy is the ability to do work or apply force to move an object. In the case of electrical charges, the force is the electrical attraction or repulsion between charged particles. We've talked about charges, we've talked about positive charges and negative charges. We will explain that positive charges attract and like charges repel and unlike charges attract. So the faster the electric charges move, the more electrical energy they carry. Electrical energy can both be created from batteries, generators, dynamos, and photovoltaics, etc., or stored for future use using fuel cells, batteries, capacitors, or magnetic field. We've already explained this. We've talked about capacitors. Capacitors are devices that store charges. We talked about it in the previous class. Thus, electrical energy can either be created or stored. So, law of conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed, only converted. But for energy to do any useful work, it must be converted from one form into something else. For example, a motor converts electrical energy into mechanical or kinetic or rotational energy, while the generator converts kinetic energy back into electrical energy to power a circuit. I'm sure you understand all this conversion. You understand how a motor converts electrical energy into mechanical or kinetic energy. You can also say a motor converts chemical energy because a car uses fuel to kinetic energy also. And you know that kinetic energy is the energy a body possesses by virtue of motion. So electrical energy conversion. This is the electrical machines, how electrical machines convert or changes energy from one form to another by doing work. Another example is a lamp, light bulb, or LED, that's light emitting diode, which converts electrical energy into light energy and heat energy. Our iron converts electrical energy to heat energy. The electrical energy is very versatile as it can easily be converted into many different forms of energy. It's just like a circle, and this energy can be converted to another. It cannot be created, neither can it be destroyed, but it can be changed from one form to another. Current. If the movement of charge is called an electric current, then we can correctly say that current is the rate of movement or rate of flow of charge. And anytime you hear rates, just know that it's something that has to do with time. Time. So he said if the movement of charge is called an electric current, then we can correctly say that current is the rate of movement or rate of flow of the charge. Then there is a relationship, that is charge per time. Once you've said the rate of something, this is the time taken for a charge to flow is what is called what? Current. The time taken for charge to flow is called current. If we select a point within a circuit, end at any point and measure the amount of charge that flows past this point in exactly 1 second. This will give us the strength of the electric current in amperes. The unit of current is amperes. The unit of current is amperes. And we already established now that current is what? Charge per time. Charge per time, because it is the movement of charge per second, and that is charge per time. The flow of current in 1 second is current. So unit of charge. The common symbol used for electric charge is the capital Q or the small letter q, basically standing for quantity. Thus, Q is equals to 1 coulomb, that is charge is equals to 1 coulomb of charge. Note that charge Q can be either be positive or negative. We've already explained this in some of our classes, how charge is positive or negative. That is it is either an excess of electron or holes. It is an excess of electron or holes. The ampere. We have seen that the unit of electric charge is the coulomb, and that the flow of electric charge around a circuit is used to represent a flow of current. However, as the symbol for a coulomb is the letter C, this can be confused with the symbol for capacitance, which is also the letter C, but charge is in coulomb, and we represent it with letter Q. Thus, 1 ampere of current is equal to 1 coulomb. 1 ampere of current is equal to 1 coulomb of charge, which flows past a given point in 1 unit of second. So 1 ampere of current is equal to 1 coulomb of charge, that is Q, which flows past a given point in 1 second, in 1 unit of second. Automatically, ampere is what? Charge per time, that is Q divided by T, that is our current. Then we can define 1 ampere A of electric current as being equal to 1 coulomb of charge per second. 1 coulomb of charge per second. The amount of charges that passes in a second is called the ampere. It's called the ampere. So 1 ampere is 1 coulomb divided by 1 second, and the formula can be Q divided by T. So if you are given a charge 20 coulomb and you are told that this charge flows in 5 seconds, you will be able to determine the current. The current then will be 20 coulomb divided by the time, which is 5 seconds, and you have your 4 ampere. Don't forget, the unit of current is ampere, the unit of charge is coulombs. The unit of charge is coulomb. So 1 ampere is 1 coulomb divided by 1 second. Is 1 coulomb divided by 1 second. The volt. As we note that energy is the capacity to do work, with the standard unit for energy being joule. A joule of energy is defined as the energy expended by 1 ampere at 1 volt. That is a joule. A joule of energy is defined as the energy expended by 1 ampere at 1 volt moving in 1 second. Electric current results from the movement of electric charge. I'm sure we already know that electric current results from the constant movement of what? Electric charge, which is electrons around a circuit. But to move a charge from one point or one node to another, there is a need for a force to create the work to move the charges, and there is the voltage. There is a need for something to push them, for work to be done, for the electric charge to move. There is a need for something to push them to do the work. We tend to think of voltage as existing between 2 different terminals, 2 different points, like point A and point B. We call it potential difference of voltage. That is the differences between 2 points. Electrons can be at point A, but we want it to be at point A. Then the work done needed to take it from that point A to point B is what is called the potential difference of voltage. We tend to think of voltage V as existing between different terminals points or nodes within a circuit or battery supply. But voltage is important as it provides the work needed to move the charge from one point to another. The charge will be at point A. That work that we need to take it from point A to point B is what we call the voltage. The voltage or potential difference between 2 terminals or points is defined as having a value of 1 volt. When 1 joule of energy is used in moving 1 coulomb of electricity charge between 2 terminals. So what is this telling us? It's telling us that our volt is the energy we need to move a charge from one point to another. So the volt is 1 joule divided by 1 coulomb. That is energy divided by charge. In other words, the voltage difference between 2 points or terminal is the work required in joules to move 1 coulomb of charge from A to B. A charge is at point A and we want it to go to point B. that the work done in pushing them from A to B is what we call the voltage difference. So therefore the voltage can be expressed as 1 volt is equals to 1 joule divided by 1 coulomb. That is energy divided by charge. 1 volt is energy divided by charge. Energy divided by charge, that is the energy you need to take a charge from one point to another, is called the voltage. Look at this picture. I want to quickly tell the difference between EMF, potential difference, and voltage. Look at it now. This is our battery. This is our charge here, staying peacefully at point Q. Here it's staying peacefully at this point, that is this point of low potential energy. It doesn't want problem. And you remember your potential energy now. It is energy a body possesses by virtue of its position at rest. So this electron is at this point Q, and we want it to go towards point P. So what do we need to do this? We need this battery. The battery is like the electromotive force. Look at the definition of the EMF. The driving force of a device that keeps the constant flow of charge across the circuit. It's just like a power that, pumping. That is what the electromotive force is. Then we now have the potential difference. The electromotive force is just like the pump that can help this charge to move from here to this point. So what is now the potential difference? The potential difference is now that difference. This charge was at this point and it was 3 joules, and now it's at this point, it's 10 joules, like energy, right? So the potential difference is just the difference between this point and this point. What has helped it to move? The electromotive force, which we are using the battery. The battery is going to send charges into the into the circuit, and this electron will become excited and leave its position of low potential and go to the position of high potential. And then the difference between point P and point Q is what we call the potential difference. So the potential difference between 2 points in electric field is the difference between this place and this. So you can see that we have 7 joules, and that gives us the voltage, and that is the energy possessed by the charges due to potential difference. This voltage is what we are going to use. Is what is usable here. Is the voltage is what is usable here. Let me explain again. You have the battery. The driving force is just like the teacher saying, read your book. Okay, you are not excelling well, you are not doing very well. It is the teacher to motivate you to leave where you are, to go to a higher point. Then the change in your result. Maybe your result before was you were having 20, then now you're having 80. The difference between your results is the potential difference. It is the potential difference, and that is the work done in moving you from this point to this point. That is the potential difference, the work done. Then the energy possessed by charge due to the potential difference is called voltage. It's because of this potential difference that there is voltage. There is a move. This energy was here, there was a difference, and that is why we have our voltage. And look at it, this is the battery, and this is just a circuit trying to power this bulb. So this question, what is the terminal voltage of a battery that expends 135 joules of energy to move 15 coulombs of charge? We've already explained. They're asking for the voltage. The voltage is just the energy divided by charge. Energy divided, and we can see that is 135 divided by 15, and we have 9 volts. That is the voltage that we need. That is the voltage we need to change the position of the charge from one point to another. They say, what is the terminal voltage of a battery that expends 135 joules of energy? That's energy that is pumping. Leave where you are, you discharge. Go to another person to move 15 coulombs of charge around the circuit. That's battery. What amount of volts does the battery need? So what's the terminal voltage of a battery that expends 135 joules of energy to move 15 coulombs? And we have gotten our volt as 9 volts. So this is another question. So simple. Let's just try to check what we have discovered from our this thing. Come in. I want to go to our board. Okay, our board. Okay, sorry. Okay, so this is our board. Control and delete. So now we've already gotten a lot of things. We've already talked about our potential difference, right? We said our potential difference is the work done to move a charge from this point to another point. It was at point P, and we want it to move to point Q, and that is our potential difference. And don't forget, we said our V is equals to the energy in joules divided by the what? The charge. So this can also be joules per coulomb. The volts can also be joules per coulomb. And we know we have our I also. What is our I? Our I is what? Q, the quantity of charge per time. Quantity of charge flowing per time is our current. And don't forget the unit of your current. The unit of your current is what? Ampere. So the current of charge. So if the charge flowing is 1 coulomb in 1 second, what is the time? The current is definitely what? 1 ampere. Is definitely 1 ampere. So let's see the example, the question we were given. He said, how much current flows through a circuit if 900 coulombs of charge passes a given point in 3 minutes. So we have charge 900, we have the time 3 minutes. So what were we giving? We're giving our charge Q, right? We're giving our charge to be equals to 900 coulombs. We're giving our T to be equals to what? 30 minutes. And don't forget, you know that the unit of time is not minutes. We are going to have to convert it to seconds, right? And how can we do that? That will be what? 30 times 60, right? And that is 1,800. Abi? So that is the what? That's going to be in seconds. So now we will ask for our what? Our current. Don't forget your current is Q over T. And what is that? That's equals to 900 divided by what? 1,800. And we have it as what? 0.5 ampere. We have it as 0.5 ampere. Okay, 900 divided by 80. Oh, sorry, 3 times 60, not 3 times. Okay, let's do our multiplication again. Oh, 30. Okay, it's 3 minutes. Sorry, I went to use 30. It was 3 minutes. Sorry, that was where the mistake came from. It was 3. So we have 180 seconds. So it's 900, right? Divided by 180. So this cancels this, and we have it as what? 5 ampere. We have it as 5 ampere. So let's go to the next question. The next question says, an electric current of 3 amperes, okay, flows through a resistor. How many coulombs of charge will flow through the resistor in 90 seconds? So we have our current and we have time. We have current and time. We have our current. We have our current to be what? And we have our time to be, let's check. Our current is 3 ampere. Our time is 90 seconds. So our current is 3 ampere. Our time is what? 90 seconds. Now we want our what? Our charge. And don't forget, I is equals to Q over T. So if we cross multiply, Q is equals to what? IT. And what is our I? 3. What is our T? 90. And that's how many seconds? That's 270 what? Coulomb. And that is the charge. 270 coulomb is the charge. 270 coulombs. And we are good to go. So we have electrical power. The what? Electrical power is the product of two quantities, the voltage and current. It is the product of the voltage and current. And so we can define as the rate at which work is performed in expending energy. The easiest way to just talk about power is about two people. You have a child and you have an adult. You give them the same amount of work. The time taken for this person to finish his own work we determine the power of the person, because you know that okay, you gave them the same type of work and the adult finished in 2 minutes, the elder person finished in 20 minutes. So power is just the work done divided by the time. So electrical power is the product of two quantities, which is the voltage and current, and so can be defined as the rate at which work is performed in expending energy. We said previously that voltage provides the work required in joules to move from one coulomb of charge from A to B. We've explained that, and our current is the rate of movement. So how are these two definitions linked together? So if V is equal to J, we already said that power is current times V. That's what we are trying to say, that power is I times V. And you know we have our V, we have our Q. So let's go and try to get it on the board. So look at it, you have your power. You said power is equals to IV, right? I times V. So what is your I? You know that you said your I is what? Q over T, right? And what is your V? Your V is what? J over C. Is that not so? That's what you have. Q over T, G over C. And that is what we are calling our power. Our power is I, which is the current, multiplied by the volt. Multiplied by the volt. So this can also be what? Q. You know, Q is just the charge. So we can change this Q to one charge. So Q will just be C, right, over T, multiplied by what? J over C. And what will that what happen there? C, we cancel C, right? Then we'll have what? J over T. We'll have J over T. Okay, let's just, we have J over T. We have J over T. So our P can now be called J over T. That is work done per second. That was what I was trying to say. Work done. The work done by the charge in a second is what is called the power. The work done by a child and the time it takes will determine the power of the child. The work done by an adult, the time taken for the adult to finish that work will determine the adult's work. And that is why power is joules per time. That is work done divided by time. The work done divided by time. Don't forget that. Work done divided by time. And so that's what we have here. So power is joules per time. I've explained that on the board. Power is joules per time. You have your V is equals to J over C and I is equals to Q over T. And then we get our power as J over T. I'm sure we understand what we explained. So we can see that electrical power is also the rate at which work is performed during 1 second. Rate, anytime you hear rate, it's just that other quantity over it. So work done by time is the power. Work done by time is power. So this is 1 joule of energy dissipated in 1 second. As electrical power is measured in watts, therefore it must also be measured in joules per second. So we can correctly say 1 watt is equals to 1 joule per second. Don't forget also from Ohm's law. Don't forget from Ohm's law. So let's just start from the, let's just try to from Ohm's law. Let's go. Don't forget that we are saying that our power is equals to what? IV, right? And don't forget your I is equals to what? Q divided by time, right? And what is your V? Your V is equals to what? E, right? Divided by what? Divided by Q, right? Divided by the charge. That's E divided by the charge. You can also call it what? J divided by C, right? You can call it J divided by C. So when we put it into this place, our high, which was Q, right, over T, multiplied by our V. What is our V? J over C. You know, then this Q is the same thing as C, right? So I can just call it C over T, right, multiplied by J over C. C we cancel C, and that's equals to what? J divided by T, and that gives us our power. So the unit of power is joules per second. So if you are giving work or energy divided by time to give you the power, and I've given you the best description. So I now said from Ohm's law. From Ohm's law, you have that V is equals to what? IR. V is equals to IR. So what can we do with this now? If our V is equals to IR, you know, we can represent it into this. So since P is equals to IV, I'm going to change my V to what? IR. So P will now be equals to I multiplied by what? This IR, right? IR. So my P will now be equals to I square R. This is another formula for the P. You can call your P I square R. So what other formula can we use for P? Also, you remember that your V, your R, okay, we can say R is equals to what? R is equals to V over I. Yes, we can say R is equals to V over I, and we can put it in this equation too. We can put it in this equation as P is equal, no, that one is going to give us our IV back. We can put our I also to be equals to what? our I to be equals to V over R. Yes, we can put our I to be equals to V over R. So here now, it's just as if we're going to be having what? V square. Abi? Because we are saying I. Let me put Control Z. We said our I is equals to V over R. Yes? So we can put it into this equation too. So P will be equals to, what is our I? V square, right? Over what? R. Then multiplied by R. No, sorry, there is an issue somewhere. Okay, V square over R square, because it's not just the V. So what will happen? R, we cancel one R, right? So P is equals to what? V square over R. So P can also be V square over R. Power can also be V square over R. Trying to get all the formulas that we can use for power. Power can also be V square over R. V square over R. So let's go back. So that's what we are trying to get here. I said we have that V is equals to IR. So if we put V is equals to IR into IV, what are we going to have? We are going to, okay, yes, this is this. We're going to have I square R. How did we do that? We change our P into IV, right? We know P is IV. Then we'll put V is equals to IR into this. And we got this formula. Also, I is equals to V over R. When we put it, and that was what we did here. Look at it. So we one R cancels one R. Then we have V square R. So those are the formulas for P. Those are the formulas for P. So if 1 watt is equals to 1 joule per second, it therefore follows that 1 joule of energy is equals to 1 watt over time. We've explained this. What this is just trying to say that power is equals to joule per second. Power is equals to joule per second. So electrical energy is obtained by multiplying power by the time in second. Thus, the unit of electrical energy depends on the unit. So if we measure electrical power in kilowatts and the time in hours, then the electrical energy consumed equals to kilowatt hour. So anytime you want to know the energy consumed, the general formula is just kilowatt hour. Kilowatt hour. So if you have watts, you have to convert it to kilowatt and then to what? Watts. So that is just what all of this is telling us. So let's see this question. A 100-watt bulb is illuminated for 1 hour only. How many joules, that's like the energy of electrical energy, have been used by the lamp? So a 100-watt of bulb is illuminated for 1 hour. Don't forget that we already said is what? Kilowatt hour. So power. Don't forget that you already established that your power is equals to joules per second. That's what I'm saying. Energy divided by time. So if I now want to look for my energy will now be equals to what? Power multiplied by what? By time. That is just what we are trying to say. So let's look at the question now. The question is saying a 100-watt bulb is illuminated for 1 hour only. How many joules? Anytime you hear joules, they are talking about energy of electrical energy have been used by the lamp. So since it's illuminated for what? 1 hour. So we know we have to convert the 1 hour to what? Seconds. So we're going to have it as power. What is our power? Our power was 100 watts, right? Then times, what is the time? 1 hour, which is 60 multiplied by 60, right? So we're going to have it as 36. That's 360,000. That is the energy. That is the energy. And the energy is in what? Is in joules. The energy is in joules. The energy is in joules. So that is what we are saying. Note that when dealing with joules as a unit of electrical energy, it is more convenient to present them in kilojoules. Okay, so we can call it 360. That is divided by 1,000 kilojoules because of how large it is. So you can call it what? 360 kilojoules. So let's check this one again. An energy uses 30 ampere of current. The resistance offered is 15 ohms. Okay, so we have that. We have this thing. We are giving the current and we are giving the resistance. So we are giving the current 30 watt ampere. We are giving the resistance to be what? 15 ohms. And we will now ask for our what? Our power. Don't forget from how we derived it, we said P is equals to IV. And since V is equals to what? V is equals to IR, then your V, V is equals to IR. So if I put this V is equals to IR into this, I can say my P is equals to what? I square R. I square R. So we can get our power from that to be equals to 30 square, right? Multiplied by 15. That is 900 multiplied by 15 what? Watts. That will give us our answer. That will give us our answer. So what is our answer? Our answer is what? 113. Okay, they said in horsepower. Oh, sorry. Calculate the power consumed by the engine in horsepower. So don't forget, horsepower, 746 watts is going to give us 1 horsepower. So now this answer was 13500 watt. So the next time we should convert it to horsepower. So 746 watts is equals to 1 horsepower. Then what about 13500 watts? What will it give us is equals to x. You know that we're going to have to cross multiply. So our x will be what? 13500 divided by what? 746. And our answer will now be in what? Horsepower. Our answer will now be in horsepower. So that is it. So our answer will now be in horsepower. We know that 746 watts is equals to 1 horsepower. So 13500 watts is equals to this, and that is our answer. So let's look at this second question. Kabiru bought 5 new light bulbs. So we're going to be taking it bit by bit bulbs, each of 50 watts. So let's do what Kabiru. Let's delete it. Control delete. We said he has a house. This is the house. Let me make the house bigger so we can draw the bulb. This is Kabiru's house, right? This is his house. Yes. Before he had 3 bulbs in the house. 1, 2, 3. And all these bulbs were 50 watts each. 50 watts. This one too, 50 watts. This one too, 50 watts. Then he went ahead to buy another one. 5. 1, 2, 3, 4, 5. They were also what? 50 watts each. 50 watts, 50 watts, 50 watts, 50 watts, and 50 watts. So now don't forget to get the energy. It's just kilowatts what hour. Kilowatt hour, kilowatt hour. So to know the energy dissipated, the energy used is the kilowatt hour. So this one was 3. So you have to multiply. That's what you have to add them together. That's either you say you have 50, right, multiplied by 3, which is equals to what? 150. 150. That was the first 150 watts because each of them were 50 watts. Then the new ones he bought is just 50 multiplied by what? By 5. And that's equals to how many watts like that? That's 250 watts. That was the total time. So I have that. What I have now is kilowatts. Then hour. They said it turned on this one for how many hours? Let me check. It turned on the new bulbs. The new bulbs for 5 hours and the old bulb for 3 hours. So it turned on these new ones, which is 5. No, the 5 ones. It turned them for 5 hours. And this one for 3 hours. So this one is equals to what? 450 what? Kilowatts hour. Right? And this one called is how many hours? Times 5. That's 250 times 5. That should be 750. Okay, 1250. So that one is what? 1250. 1250 what? Kilowatt what? Hour. Kilowatt hour. So no, it's not yet kilowatt hour. 1250 watts. Sorry, we've not divided it by 1000. So that's 150 watt hour. So if I add these two together, that will be 1250 plus what? 450. So we have 0, we have 0, we have 7, we have 1. Is that correct? 7. Okay, so 1700 divided by what? 1000. This cancels this, this cancels this. So that will be what? 1.7 what? 1.7 kilowatt hour. So is this 1.7 kilowatt hour? We will now multiply by the amount. This is 200 per unit. So it will be 1.7 multiplied by what? 200. Is all about that. Then your assignment, this is the assignment. You can solve it because we've done a lot of examples on that. Thank you. See you in the next class.